All right, so today we're going to be learning about rational functions. So this first slide is for you to read through, take notes, some definitions here. What is a rational function? It is a function that can be written in the form p of x over q of x, where p of x and q of x are polynomial functions. So we just studied polynomial functions. We know they could be any degree. So we are now just pretty much dividing two functions, okay, two different polynomial functions, okay, and rewriting it in rational form here, so as a fraction. When you're looking at a rational function, some key features are always the x-intercepts. The x-intercepts will be what makes the numerator zero, the top, the p of x. So you just set p of x equal to 0 and solve, and you could find your x-intercepts. There's a little caveat on that. If that value also makes the bottom 0, then it's not an x-intercept anymore, it becomes a whole, which we talk about now. When the denominator equals 0, those are called points of discontinuity. So denominators can never be 0. So if there's any values that make the denominator 0, we're going to have points of discontinuity. There's two types, vertical asymptotes and wholes. The vertical asymptote is like a wall. It's just a vertical line. We represent it with a dashed line on the graph, and the graph is going to approach it but never actually equal that x value. And again, if the value makes the bottom, the denominator 0, so q of x, right, whatever makes that 0 is going to be a point of discontinuity, a vertical asymptote. If there's a value that makes both the top and bottom 0, it is a whole. All right, so it's just an undefined point on the graph. And I call it a point because we actually represent it, which is a blank circle. I guess it's not really a point, all right, but we could write it as an ordered pair. So you simplify your rational function, you plug in that value, and whatever that y coordinate is will be the y value of your whole. All right, so we're going to look at some examples with all that stuff. Okay, so here's just an example. All right, here's a rational function that looks like this. All right, there you got a polynomial function on top, you got a polynomial function on bottom, right? Third degree on top, second degree on bottom. So you're looking at the graph here. This red dashed line is the vertical asymptote. So at 3, if I plugged in 3 into the bottom, it would make the bottom 0. All right, so we have a vertical asymptote. You see there's a hole right here, okay? And that's if I plugged in 0, it also makes the bottom 0, but it also makes the top 0. All right, so if I plugged in 0, right, you can see that x was a common factor in both of them. Okay, so 0 is a whole because it makes both the top and bottom 0. See your x-intercepts at -2. If you plug in -2, that's going to make the top 0, and 4 will make the top 0. So we got to identify all these features by just solving the numerator and denominator set equal to 0. All these other features we just get from a table of values. Okay, here are the steps. Okay, we're going to start by factoring the top, factoring the bottom. Right, then once it's in factored form, we could easily solve when it equals 0. Right, p of x will give us the x-intercepts. Right, solving q of x, the denominator, gives us a vertical asymptotes. A little parentheses here, right? If it makes both of them 0, then it's a whole. All right, we simplify the function by canceling out any common factors. If we have a common factor that cancels out, right, one that had an x in it, that's when you're going to have a whole. Right? If no x's cancel out, then there's not going to be a whole. Right? We find the coordinates of the whole by plugging those x values into the new simplified function. So whatever made the original function 0 on top and 0 on bottom, we plug into the new simplified function, and then that's our y coordinate. Right? Then we can find the y-intercepts by plugging 0 into the new simplified function. All right, and so now we have the x-intercepts, we have the y-intercepts, we have the wholes, we have vertical asymptotes. All right, we can plot all those on the graph. All right, and then we just make a table of values to find enough points to help sketch the rest of the graph. All right, so we have our first one here. We'll do an example. All right, so it says find the x-intercepts and points of discontinuity for f of x. All right, so we're going to go ahead and factor the top and bottom here so we can graph this. And so the top is going to be x minus 3, x plus 1. On the bottom, I'm going to take out a -3, and I'm going to get x minus 1. Okay, so notice nothing cancels out, so there's not going to be any holes. All right, so I'm going to have a vertical asymptote at what makes the bottom 0, so that'd be positive 1. And I'm going to have an x-intercepts at positive 3 and negative 1 because that's what makes my numerator 0. So x-intercepts, okay, there's 2 of them, positive 3, 0, and negative 1, 0. All right, my vertical asymptote, I'll just abbreviate that VA, okay, is what makes the bottom 0, so that's just x equals 1. Remember, we write it as a line, a vertical line, so it's always x equals. All right, so we have our point of discontinuity is the vertical asymptote, and we have our x-intercepts. All right, so if we go to graph that, all right, I can plot those points. So over here, I'm going to plot my x-intercepts, which were 3 and negative 1. I'm going to draw a vertical asymptote at positive 1. Just a dashed line. All right. So now I have all that done. I want to find my y-intercept. So my y-intercept, I just plug in 0. Right? What is f is 0? All right. So I plug in 0 into everything. Right? You get 0 squared. Again, you don't really need to write that. You know that's 0. Minus 2 times 0. Again, you don't have to write that. That's 0. Minus 3 over negative 3 times 0 plus 3. And so really we just get negative 3 over 3, which is negative 1. So I have a y-intercept at negative 1. So 0, negative 1. So I'll plot that point. All right. And so I'm going to now I need to plug in a point. Okay, I think the graph is going to come down like this, but I just want to make sure. I'm going to plug in some points here on a table of values. I'll probably want to plug in positive 2 to see if that's down there or up there. I could plug in positive 3 over here to see that it's going up to make sure that's what it's doing. So I want to find, or sorry, that's negative 2. So I'm going to find f of negative 2. And I want to find f of 1, or f of 2, positive 2. All right, and those should be enough for me to figure out my stuff. So, you know, if I just plug it in, I'll kind of verbalize it. So negative 2 squared is 4 minus 2 times negative 2, so that's going to be plus 4 minus 3. On bottom, negative 3 times negative 2 is 6. 6 plus 3 on bottom, so I'm going to get 8 minus 3 on top, which is 5. 6 plus 3 is 9, so it's positive 5/9. So it is going to be going up. So my graph over here is going to look something like this. Remember, as it gets to the asymptote, it never actually equals it. It just gets really close and will go down forever. All right. Remember, if you draw to the window frame, you don't need arrows. Okay. Over here, if I plug in positive 2, I'm going to get 4 minus 3. And then negative 6 plus 3. So on top, I'm going to get negative 3. On bottom, I'm going to get negative 3, so that's positive 1. So at 2, it's 1. So now I can see that this graph on this side will look like this. And again, if you need more points or you're not sure how I'm knowing the curve is going to look like that, you can plug in as many points as you need to make sure if you wanted to plug in 5 or 10 or whatever. Okay, the more points you have, the more accurate your graph is going to be. And so you can see, right, it's pretty comparable there, where I've got my axis of symmetry, or my vertical asymptote, and my lines there. Okay, right at 1, my x-intercepts are 3 and negative 1, so everything looks really good there. Okay, so what's the domain? All right, so the domain, we're going to go ahead and use interval notation to write it, but again, you're talking about your x value. So it goes left forever, it gets to 1, it never actually equals 1, right? But then it continues on forever after that. So it's all real numbers except for 1. And so we're going to write that in interval notation. All right, so we're going to go negative infinity parenthesis, not 9, to 1, and never doesn't equal 1, so it's going to be parenthesis. And then I'm going to go union, and start at 1 again, and then go to positive infinity. All right, and so all real numbers except 1, so you just write it just like that. All right. All right, so next problem. Okay, same thing. I'm going to factor the top and bottom. So the top has a GCF of an x. I'm going to take out that x. That leaves me with x squared plus 3x plus 2. And then on bottom also has the GCF. That's going to be 4x. That's going to leave me with x plus 3. I can still factor on top. Okay, so I'll keep going here on top. So that's going to be x plus 2, x plus 1. All right, and so now I'm looking, okay, can I cancel anything out? And this one I can. I could cancel out the x's. There is a GCF, okay, and so I'm going to cancel these out. This means that there's a hole, okay, at whatever makes that 0, and that's 0, right? There's x, so at x equals 0, there's the hole, okay? So there's a hole at x equals 0, but I also want to know the actual point. Okay, so I need to take my final simplified version, so I'll rewrite this as simplified as I can. X plus 2, x plus 1. Let me get that a little bit neater. Okay, so I have it in simplified form. I've got to plug 0 into that, okay, to find my hole. So when I do that, right, it's just going to be 2 times 1, so 2 on top and 12 on bottom. So I'm going to get a 1/6 there. So my hole is at the point 0, 1/6. All right, and so again, where did 1/6 come from? I just plugged in f of 0, okay, into the simplified red version. All right, and when I do that, I get 1/6. All right, so what are my x-intercepts? So my x-intercepts are what makes the simplified version 0 on top, and so that'll be -2, 0, and -1, 0. All right, and then my vertical asymptote, what makes the denominator 0, and that's going to be -3. So x equals -3. So I have all my points of discontinuity, a hole and a vertical asymptote on my x-intercepts. All right, and so I'm ready to sketch a graph. All right, so I'm going to plot my two x-intercepts, which were -2 and -1. All right, I'm going to plot my vertical asymptote at -3. And then I know I have a hole, okay, at 0.16, so I have a hole, okay, really close to the x-axis there. So what I need to do now is, I don't know is this going to be like a little U type of thing? Is it going to be coming up? So I need to really, if I plug in a number right here that's close to this asymptote, all right, to make my table of values, so like -2.5, okay, I'm going to find out, right, that it's going to be a positive number. So I know it's going to end up being up here. All right, and so my graph should look something like this. It's going to come down through, come back up. Okay, and hit my graph something like that. Okay, but what's going on this side of the asymptote? So I do need to kind of plug in -4, probably a couple numbers here. If I plug in -4, All right, so negative 4 cubed is negative 64. And 16 times 3 is 48. And then 2 times negative 4 is negative 8. And then if I plugged in negative 4 on the bottom, that's 16 times 4, that's positive 64, minus 48. So negative 64 plus 48 minus 8 is going to be negative 24. And then 16 minus that is just 16. 64 minus 48 is 16. All right, so negative 24 over 16, which is just negative 3 over 2, or 1.5. All right, so at negative 4, I'm going to get a negative 1.5. And I just need to plug in negative 5 as well. Yes, I could also plug it into the simplified version as well, if that's easier to plug into, which it definitely looks like it would be. Right, so if I plugged in negative 5 into my simplified version, okay, so let me rewrite the simplified version over here. All right, it was x plus 2, x plus 1. Over 4 times x plus 3. If I just plug in negative 5 into that, okay, what's f of negative 5? So now I get negative 5 plus 3, that's negative 3. Negative 5 plus 2 is negative 3, times negative 5 plus 1 is negative 4. So just a 12 on top. Then negative 5 plus 3 is negative 2. So 4 times negative 2. So I'm getting 12 over negative 8, all right, which is negative 3 over 2. Which is going to tell me, since that end behavior is going up, so that's going to tell me that this one is going to be, here is going to go a little bit above it. Remember, we can't go through the X-intercept again, and back down. Okay, so I got a graph like that. Okay, we can compare. And that looks pretty darn good. All right, now what's the domain? Okay, so the domain, I'm going to have all real numbers except negative 3 and 0. We got to remember the whole as well. So all real numbers except 3 and 0. So I'm going to go so from negative infinity to negative 3. I'm going to have the union, and then I got to go from negative 3 to 0. And these are all going to be parentheses because these endpoints are parts that are not part of the domain. And then I need to go 0 to infinity. And so you got to break it up. So again, you read that all real numbers except negative 3 and 0. Right, and that's how you write it in interval notation.